The tensile force of the pre-stressing steel, whether it is cable or bars, will be subjected to force losses. The losing of pre-stressing tensile force will reduce the capacity of the structural member. Therefore, pre-stressing losses should be calculated and compensated in the jacking force. Jacking force magnitude is equal to effective pre-stressing force plus the expected pre-stressing losses. There is a different type of losses such as friction losses, elastic shortening, relaxation of pre-stressing steel, and others. The first type of pre-stressing losses is friction and wobble losses. Friction losses occur due to the friction between strands and the duct. Friction losses are related to the angular change of duct profile. The friction losses will increase by the increase of angular change of duct profile. At the time of pulling a tendon, the friction of tendon with the duct will reduce the force in the tendon. The coefficient mu used to predict friction losses. However, the use of mu alone is not efficient. Therefore, another coefficient K or wobble coefficient used to account for an intended friction between strand and duct as a result of an intended duct misalignment. The friction loss can be calculated using the following equation: delta F equal F times 1 minus E 2 minus Kx minus mu alpha, where Fbg is the stress in the pre-stressing steel at jacking, X is the length of a pre-stressing tendon from the jacking end to any point under consideration, K is the wobble coefficient, mu is the coefficient of friction, alpha is the sum of the absolute values of angular change of pre-stressing steel path from jacking end or from the nearest jacking end if tensioning is done equally at both ends, to the point under investigation. E is the base of Neperian logarithms. Friction losses occur in post-tensioning only. In pre-tensioning there is no friction loss because we don't have ducts and the cables stressed before casting of concrete. Anchor set occurs when the jack releases the tendon after achieving the required jacking force. When the tendons are released, the wedges will be pushed slightly back and seated in position, as shown in this figure. The amount of wedge movement is termed as anchor set. The movement of wedges will result in reducing the force in tendons. Tensioning a tendon will increase the length of the tendon, but when the wedges are seated, the internal tension force of tendon slightly reduces. This type of loss will affect a portion of the tendon, as shown in this figure. This figure is showing an example of an anchor set. The shaded area is the area of anchor set loss, and we can see in this figure the point of zero movements where the anchor set is not effective and not causing any losses. In the pre-tensioning method, there is no anchor set loss because wedges are not used. As we know, the pre-stressing force will compress the concrete members. The compressing of a concrete member will reduce the member size. This is known as elastic shortening of concrete. Elastic shortening of concrete will increase the length of the tendon, which results in reducing the internal tensile force of tendon. The elastic shortening is accumulative for the post-tensioning method. The stressing of the first tendon will cause elastic shortening and reduce the pre-stressing force for the first tendon. The stressing of the second tendon will cause pre-stressing force loss for the first and second tendons together, and so on. In pre-tensioning members, when the tendons are cut and the pre-stressing force is transferred to the member, the concrete undergoes immediate shortening due to the pre-stress. The tendon also shortens by the same amount, which leads to the loss of pre-stress force. Elastic shortening occurs in post-tensioning and pre-tensioning. Concrete shrinkage, defined as the contraction of concrete due to the loss of moisture. The losing of pre-stressing force will be a result of the reduction of the concrete member dimension, which increased the length of the tendon as in elastic shortening and anchor set. Concrete shrinkage is a time-dependent loss, and it is increasing by the time. Curing the concrete adequately and delaying the application of load provide long-term benefits with regards to durability and loss of pre-stressing force. The calculation of concrete shrinkage can be done using this equation from the ASHTO code. As we can see here, a lot of coefficients are required, such as volume to surface ratio factor, humidity factor, and others. Concrete shrinkage occurs in both post-tensioning and pre-tensioning. Creep is also a time-dependent loss. Creep of concrete is defined as the increase in deformation with time under constant load. Due to the creep of concrete, the pre-stress force in the tendon is reduced with time. Curing the concrete adequately and delaying the application of load provide long-term benefits with regard to durability, loss of pre-stressing, and deflection. The calculation of concrete creep can be done using this equation from the ASHTO code. Creep occurs in both post-tensioning and pre-tensioning. Relaxation of steel is another type of pre-stressing loss. Relaxation of pre-stressing steel occurs due to constant strain. The pre-stressing steel will elongate slightly under constant strain after a certain time, which results in pre-stress force loss. Due to the relaxation of steel, the pre-stress in the tendon is reduced with time. The relaxation depends on the type of steel, initial pre-stress force, and the temperature. Relaxation of steel occurs in both post-tensioning and pre-tensioning.